Hey guys, it's Miss Johnson and I'm here to bring you our notes for section 8.3. In section 8.3, we're going to start looking at calculating a confidence interval for two proportions, for two samples. So we want to talk about the conditions and talk about how we would calculate that confidence interval. So the sampling distribution of a difference between two proportions. This little box right here comes from section 7.2. We talked about how to combine proportions. We added them and we also subtracted them. So we're looking at subtraction of proportions. We're looking at a difference of proportions in this section and how we do a confidence interval of them. But I just want to refresh your memory on where do we get the mean and where do we get the standard deviation. And also, how do we determine that the population is approximately normal? Because we can't do any of this unless our population is approximately normal. So the first thing is to determine that the population is approximately normal, we have to visit that large counts condition. We have to make sure that it's met for both samples, which means we need the first sample times p to be greater than 10, and the first sample times its 1 minus p to be greater than or equal to 10. The second sample times p to be greater than or equal to 10, and the second sample times its 1 minus p to be greater than or equal to 10. All four things have to be true. Once all four things are true, then we can call it approximately normal, and we can move on. The mean of this difference of proportions is just when we subtract the proportions. That's it. All we have to do with those is subtract the proportions. The standard deviation, that's the one that got a little bit tricky for us. We never subtract standard deviations. What we do every time is we add their variances. So you can see that we have the proportion times the 1 minus proportion divided by n, proportion 2 times 1 minus proportion 2 divided by n, and we add that, and then we take the square root. Okay, so we're adding the variances and taking the square root in order to get the standard deviation. We also have to state this. We have to state the 10% condition for both proportions, for both samples. Okay, so it's a lot of conditions to get checked off. So just heads up on that. We're going to practice one on the next slide. So in this question, we're just going to practice meeting the conditions and putting the mean and the standard deviation together. So it says your teacher brings 2 bags of colored goldfish crackers to class. Bag number 1 has 25% red crackers in it. Bag number 2 has 35% red crackers in it. Each bag contains 1,000 crackers. Using a paper cup, your teacher takes a simple random sample of 50 crackers from bag 1, and a separate SRS of 40 crackers from bag 2. Let p hat 1 minus p hat 2 be the difference in the sample proportions of the red crackers. So the first thing is, what is the shape of the sampling distribution? Okay, so in part A, the first thing is we're going to try and prove this thing approximately normal. That's our goal here. So if we can prove that the proportion times the sample size is greater than or equal to 10 for all 4 of those parts, then we're good. So I'm going to start with N1 times P hat 1, which would be 50 times 0.25, which is 12.5, greater than or equal to 10. Okay, great. How about N1 times 1 minus P hat 1? That's 50 times 0.75, which is 37.5. Great. Those two are good. Now let's go to the second proportion, or the second sample. So N2 times P hat 2 is going to be 40 times the second bag at 35%. I lost that for a second. Times 0.35, which gives me 14, which is greater than or equal to 10. Great. Then the 1 minus P hat 2 is equal to 40 times 0.65, which is 26, greater than or equal to 10. All 4, check, 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 check. Those are all good. So we can say, because all values are greater than or equal to 10, I'm going to just use my symbols here, greater than or equal to 10, the sampling distribution of p hat 1 minus p hat 2 is approximately normal. Notice that I said the sampling distribution of these two. I didn't say that p hat 1 minus p hat 2 is approximately normal. I said the sampling distribution of them is approximately normal. That's important because we don't actually know what the shape of p hat 1 minus p hat 2 will be, but we know what the shape of the sampling distribution will be because of these four things. Okay, so our sampling distribution, where we have the 50 crackers in one sample and the 40 crackers in the other sample, when we take that sampling distribution, meaning we repeat the process over and over and over and over again, that shape will be normal. Okay, now let's go on to B. In part B, it says find the mean of the sampling distribution. All right, so now that I know that it's normal, I can say that the mean is going to be the mean of p hat 1 minus the mean of p hat 2 is going to be 0.25 minus 0.35, which is negative 0.1. And yes, it's okay to have a negative mean here because it's a difference in means. So you can have a negative difference. All right, now let's go on to part C. So in part C, now we want to calculate the standard deviation. So calculate and interpret the standard deviation. So for the standard deviation, the first thing I need to know is, do I meet the 10% condition? So my sampling size for N1, or for my first variable, is 50. 50 is less than or equal to 10% of 1,000. Okay, check. N2 is equal to 40. My sample size for sample 2 is equal to 40, which is also less than or equal to 10% of 1,000. Okay, check. So those two things are true, which means that I can then plug the values into my standard deviation equation. So if I do that, I'm going to have the standard deviation of p hat 1 minus p hat 2 is equal to, I got a long radical here. So I need to deal with the first sample. So I have 0.25 times 1 minus 0.25, or in other words, 0.75. All divided by the sample size, which is 50. And remember, I'm adding these because we don't subtract standard deviations. We add the variances. 0.65, all divided by its sample size of 40. And then I'm going to go ahead and plug all of that into my calculator. Just be careful with your order of operations there. So I like to do things in pieces. That's just my style. If you're really careful with parentheses, then you can probably enter it all in together. I don't do it that way because I don't trust myself. And I like my calculator to do a lot of that work for me. So I do it in pieces. Divide it by 40. So then I'm going to arrow. And again, I have a calculator that I can arrow up and hit enter on things, which makes it a lot easier because you don't have to retype a lot of stuff. So I'm going to add those two things together, and then the second square root, second answer, and I get 0.097. So my standard deviation there is 0.097. All right. Remember that a key piece of this was to interpret. So I'm going to write, I always run out of room, you guys, I'm sorry. So I'm going to write really small up here for my interpretation. The difference in bag 1 minus bag 2 of the sample proportion of red crackers will typically vary, or typically varies by 0.097 with, and then state your mean. Mu of p hat 1 minus mu of p hat 2 equaling negative 0.1. Okay, that's my interpretation. So I talked about what I'm looking at. I mentioned that I'm taking bag 1 minus bag 2. I talked about how it's a sample proportion. It's a sample and it's a proportion. We're not looking at sample means, and we are looking at samples, so make sure that's true, or make sure that's in there, of red crackers. Typically varies. That tells you it's standard deviation. Put your standard deviation in. List your mean. Those are all the important pieces. Okay, that was just conditions, you guys. Just conditions. So we stated the conditions, we stated the mean, we stated the standard deviation. We didn't even get into the confidence interval yet, so hang tight. So now let's talk about a confidence interval. So it says many interesting statistical questions involve comparing the proportion of successes in two populations. It's common to look at two populations against each other. What is the difference between proportions of Democrats and the proportion of Republicans who favor the death penalty? How has the proportion of teenagers with a smartphone changed from 10 years ago? In both of these cases, we want to estimate the value of P1 minus P2, or proportion 1 minus proportion 2, where P1 and P2 are the proportions of successes in the two different populations. Other statistical questions involve comparing the effectiveness of two treatments in an experiment. That is a big piece when we get into significance tests. We're going to talk about treatments a lot. For example, how much more effective is a new medication for relieving headaches? What is the difference in survival rate for two different cancer treatments? So we compare two things a lot. That's the basis here. We are often looking at how much more effective or better is one thing versus the other. So when we are doing the confidence interval for these two things, we have to make sure that we check all of these conditions just like we did when it was a confidence interval of one sample. We have to state that both random samples were done independently and done randomly. We also have to state the 10% condition for both samples. So you're going to list this 10% condition twice. We also have to do the large counts rule like we just talked about for both samples. So the n times P1, n times 1 minus P1, n times P2, n2 times 1 minus P2, they all have to be greater than or equal to 10. All right, so now let's check the conditions and actually get into calculating the confidence interval. So it says a Harris Interactive survey asked independent random samples of adults in the United States and Germany about the importance of brand names when buying clothes. Of the 2,309 U.S. adults surveyed, 26% said brand names were important, compared to 22% of the 1,058 German adults surveyed. So let PU be the true proportion of the U.S. adults that think they're important, and PG, P sub G, be the true proportion of German adults who say they're important. Check the conditions for calculating a confidence interval for whether these two things are equal are met. Okay, so here's our conditions. So first of all, random. Okay, random selection was used in both samples. This is a simple one usually. So asked independent random samples of adults from the United States and Germany. This was stated. Great, check, done. Random selection was used for both samples. For both samples. As stated. Great. Okay, moving on. 10%. Okay, let's move on to the 10% condition. So for the first sample, my N for the United States is 2,309, which we can all agree is less than or equal, is just less than 10% of all U.S. adults. And then the N for G, for Germany, was 1,058. Now, I'm not super familiar with the population size of the country of Germany, but I'm willing to bet that there are more than 10,580 adults. So we're going to say that that's less than 10% of all German adults. Done. Check. Okay, 10%. Next, large counts. Here we go. This is the one where we got to do this 4 times. Large counts. So I need NU times P hat U, which is 2,309 times 0.26, which is 600, roughly 0.34, which is greater than or equal to 10. Great. Then NU times 1 minus P hat U is 2,309 times 0.74, which gives me a bigger number. So great, good, check. Then NG times P hat G, 1,058 times 0.22 gives me 232.7, greater than or equal to 10. Then NG times 1 minus P hat G, 1,058 times 0.78, and again, a bigger number, 825.2, greater than or equal to 10. So the large counts condition is met for both samples. And again, this is just checking conditions. We haven't even gotten into calculating the confidence interval yet. Whee! Gear up. You're doing great. All right, so let's talk about the statistic plus the critical value. So we're going to get into the equation now for the confidence interval. So the statistic plus the critical value times the standard deviation of the statistic. For your statistic, you need the difference in the means. That critical value is the same as what we found when it was only one sample. So you're looking at, if you're 95% confident, you've got 2.5% on either side. If you're 90% confident, you've got 5% on either side, and you find the z-score that's matching to it. The standard deviation of the statistic comes from that standard deviation, okay? So once we prove, so we don't know the standard deviations for the true population. That's not something we can find. But once we prove that we can use normal statistics here, we do the large counts and we have all the conditions met, then we can use the p hat values. Okay, so we use p hat 1 and p hat 2 to estimate the standard error. That's why they call that SE, the standard error, because we don't know the true standard deviation. But we can estimate the standard error once we've proved all the conditions, so we know that we can use normal calculations. So here is the formula, once again, for when all the conditions are met, a C confidence interval for the difference between proportions looks like this. And one more time, this is going to be given to you on the formula sheet. So you don't have to have this equation memorized. You just have to know where to apply it. That's the biggest piece, okay? All right, so we're going to stop there for now, and we will come back in the next video and actually do one of these big, long confidence intervals. So thanks for tuning into the first part, and I will catch you next time.